talk is by Miguel Evangelista-Alvarado, who will speak about tutorial on computational Poisson geometry.
Okay. Can you hear me?
Yes.
Yes. Okay. Thanks to the organizers for accepting the talk. Let's start. In this talk, we will address a small tutorial of Python modules, Poisson geometry, and numerical Poisson geometry. Hence the title of the talk. This work is a collaboration with my advisor, Pablo Suárez Serrato, and José Ruiz Pantanio. Due to time constraints and the fact that everyone is expert in Poisson geometry, I will go directly to explain our models. Poisson geometry is a model written in Python that performs local Poisson integers calculation in Poisson manifolds in the symbolic sense. Ours is an open source and it's available in GitHub. This link does it, each of the methods can be audited, and in case the user cannot find a method, you can have use developed and run by users. Or you can develop the method on your own and require to add to the model through a pull request. So click. And this is GitHub repository to Poisson geometry model. And you maybe pull request and issues. And you load the code in this file. And this file contains all the methods on the models. Okay. Okay. Poisson geometry is divided into two types of methods. First is symbolic calculation, that's it, methods that make a split calculation, and set methods that verify a property, that's it, methods that return a Boolean value, that's it, the value is true or false. The model uses SymPy as backend. Therefore, the model has the computational limitation that SymPy has. Why SymPy? Because it's free, it's Python, it's lightweight, and many projects use it, like SageMatch, for example. In the following table, we can see all the methods that are in the model. For example, the calculation of the matrix associated to a bivector is bivector to matrix. The calculation of the p-chamorphins and chamorphins, or the complementary operator associated to bivector, complementary operator. Now, methods that verify a property are verify if a function is Casimir, or verify if a bivector is a Poisson or no, is a Poisson tensor. Now, this function requires checking where a symbolic expression is zero. Therefore, they are naturally limited by computational theoretical of symbolic calculus. In resume, it is worth mentioning that four of methods of Poisson bivector will be need as parameter, and depending on the method to be performed, other parameters will need. The second model, the numerical Poisson geometry, is a numerical version of the Poisson geometry model. That is, with the model, it's possible to evaluate a point cloud in submethods of the Poisson geometry. For example, evaluating a matrix associated to a vector, yes, num bivector to matrix, or evaluate the Hamiltonian vector field associated to Poisson bivector, num Hamiltonian VF. It's the same case. This model is auditable, and you can load the code in this link. Functions that are marked with asterisk mean then they explicitly depend on the symbolic model. That's it. Now, this is a symbolic evaluation. Sorry. For this reason, the evaluation may take longer, obviously also depending on the point cloud we are working with. And the functions that are not checked are optimized because they allow matrix operation that are already optimized in NumPy. It is worth mentioning that the backend of this model is NumPy. The source code is also available in GitHub repository in this link. Okay. We believe that the numerical model might be an application in machine learning. Okay, go to tutorial. Scan a QR code to open a Google Colab and a new tab in your browser so that you can do tutorial with me. Okay. Colab is a Google platform that allows you to make projects in Python language without the need to install anything on your machine. Our models are available for Python. It's very easy to install them by running the following. To run this solve to install the Poisson geometry and numerical Poisson geometry models. Okay. Now we have the models already introduced in our Google Colab. For the Colab to display our results in lattice property, we run the following. Remark: in our function of Poisson geometry model, it's also possible to find the lattice code of the results by adding the parameter lattice equal true. As function name param, the last param lattice equal true. Now we explain the syntax with which we can deal with Poisson models. Let's start a scalar function. A scalar function is writing using a literal expression. For example, look this function and look this expression in Python language. For example, is 8, x1, asterisk 2. This is the relationship. The second, plus b x2 asterisk 2, b x2 power 2, plus c x3 asterisk 2. This is okay. This is the relationship make to the communicate the word real expression to the Python expression. Here, x1, x2, and 3 are symbolic variables that the Poisson model, Poisson geometry defines by default and represents, in this case, the coordinates x1, x2, x3. All symbols that are not local coordinates are treated as symbolic parameters. For example, A, B, C. In this table, we show that the Python supports the following basic operations. Look. Okay, a multivector field or differential from the Poisson geometry is written using Python dictionary, where Python dictionary the structure is k value. And then the k is array. The k is array and contains the order of the index on the base elements, and the value is the notation of the coefficient that accompanies this base element. For example, x1, for example, for this vector field, x1 it's 1. Index 1, 1. It's 2, it's 2. Index 2, index 2. It's 3, it's 3. Index 3, index 3. Now, for the vector field, the comma in case important because it's Python syntax to arise. For the vector fields, it's the same. It's 1, it's 1, index 1, index 2, index 1, index 2. Minus, it's 2, index 1, index 3. The same for the last element. And it's the same for the 3 multi-vector field. No, it's 1, 1, 2, 3, 1, 2, 3. Okay, and remark, we can only write the grades and values of non-zero coefficients. It's not necessary. And it's necessary this remark. We change the order on the index and H2 and in the minute sign in the corresponding street value. For example, it's 1, index 1, index 2. But I change the order and the indices, the dictionary change, and the case is 2, 1 minus x h1. That this expression is related with this expression. The syntax for the differential form is the same as for multivectors. Then the user must be aware when using a multivector or differential form, depending on the method being used. Okay, testing the Poisson geometry and numerical Poisson geometry classes. We import Poisson geometry and numerical Poisson geometry class, like any Python model. As the name is long, we can put alias like NPG or PG for simplicity. That's it. Okay, the model was the following, in this sense. And put the alias and need one parameter. The first parameter is mandatory and is the dimension in which we are going to work. The second parameter is optional and defines the variable we will work with. The default value is x. Okay, but you put any symbol, a, for example. As the numerical model uses a point clouds to perform evaluations, then to create a random point clouds with numbers. We will run the following. Okay, in this sentence, the first argument is the number of the points, and the second argument is the length of the vector. Example 1, 2, 3. No? Is the vector to the length is 4. Okay, let's start to the tutorial. The idea of this tutorial is verify already known facts of the Poisson geometry by means of some examples. Example 1. In this example, we calculate to associate matrix of a bivector, evaluate it on the point cloud. Check if it's a Poisson vector, bivector, sorry, and calculate the Poisson bracket. Okay, the matrix of the bivector field on R4 defined as P can be decomputed as follows. Import the class, define my space, and write bivector. look, it's 3, index 1, index 2. Minus, it's 2, index 1, index 3. Okay, and use the function by vector to matrix. This function only nets by vector param. Run the solve. This is the matrix associated 3 by vector. Remember, if one way the lattice count, only add the flag lattice equal true. And the result is the lattice count. On the matrix, the power of the lattice flag is that you copy and paste the result into text file. Okay, to evaluate the vector in the point cloud M uses the numerical evaluation. And then MPG4 okay, sorry, syntax error. MPG4 is from no Poisson, and give me 1 second. Sorry. Okay, import the class, define the class, and evaluate in the point cloud M. Okay, and evaluate the by vector in the point cloud M. This method, we can add the flag torch output, TensorFloat output, or the dictionary output, no? Equal to true to obtain the specific arrays. The result is a NumPy array by default. Okay. Also, it's possible to verify that P is a Poisson by vector. Run the cell, result is true. This is the type of functions to the returns a Boolean value. Check this domain. The implementation of the test type methods requires checking where a symbolic expression is zero. These are naturally limited by computational theoretical constraints. Now, we compute the Poisson bracket FH as follows. Define F and H and calculate the Poisson bracket. The result, H3. Look, check. H1, H2. H1 is true, the result is H3. Okay, and we also obtain the result in lattice code. Sample 2. In this example, we check that function is a Casimir or a Poisson by vector. And if a vector field is a Poisson. Consider the lead Poisson by vector field in a tree. And the Casimir function K, given by this expression and by vector this expression. Okay, import my module, Poisson geometry, define the module in the dimension tree, and write a vector Python dictionary syntax, and write the function K, and use its Casimir function. Result is true. Okay, this verifies that in effect, in the chat, Oh, sorry, I have it wrong. This is the finding. Okay. And we have the Hamiltonian vector field. No, sorry, vector field. This this field is not Hamiltonian. Only write this expression in Python dictionary syntax and use this function. No, is Poisson vector field. Okay. We can check the results in the Nakashishi course. Okay. Time is over.
Miguel, can you hear us?
Yes.
Miguel? So you have 5 more minutes, okay?
Yes. Thank you.
Yep.
Okay. It's example 3. In this example, we only compute the Hamiltonian vector fields. Both ways is to show that the model is of Greek half with non-large numbers. For example, consider the Poisson by vector in R6 given by, and the function given by function h, and then the Hamiltonian vector field of the h in respect to p is given by this expression. Okay, with the Poisson model, the Poisson geometry model, is possible to calculate this Hamiltonian vector field. How? Import my model, define the dimension, write by vector, write h function, and calculate Hamiltonian vector field. The result, this is. Okay, example 4. In this example, we calculate the modular field associated with a Poisson by vector. Okay, consider by vector given by in R4. This bivector field arises in the analysis of the orbital stability of the phase envelope oscillator in R4. Okay, this bivector you can find in the Averaño Camacho Vallejo work. For computate the modular vector field P with respect to volume form F omega 0 in R4, where F is a non-zero function and omega 0 is a Euclidean volume form in R4. Okay. Therefore, in this case, the modular field of P with respect to the Euclidean volume form is trivial. Okay, import the class, define the class, and write in by vector, and use the function modular vector field. Okay, the second input on the modular vector field function in the last example can take any real function to modify the volume shape. Okay, check is on modular homogeneous, and this can also verify numerically. Import numerical Poisson geometry, import define numerical Poisson geometry, define the point cloud, and evaluate the modular vector field in the point cloud M. With the array is a torch tensor type. Okay. Okay. The last example, we calculate the Hamiltonian vector field associated with a function f and the Poisson vector and show its graphical. Okay, I'm given, consider the bivector, consider the most function, how to calculate the Hamiltonian vector field, import Poisson geometry class, define the Poisson geometry class, write bivector, write function, my smooth function, and calculate Hamiltonian vector field. And the time is over. Yes. Only show the last results. Okay, that's it.
Thank you very much. So let's thank the speaker. So questions, please. Any question? Yeah? Question? No?
The bibliography.
Hi, this is so I was curious, is it possible to use this module for calculating just like Lie brackets of vector fields? Is that like something that's included in it, or is it like say you just have some vector fields defined over, with like polynomial coefficients or something, you want to calculate the Lie brackets algebra?
Okay. No. I think in this case, no. But to calculate the Hamiltonian vector field, only need Poisson by vector and a small function. But the most function can be write in Python syntax.
Okay.
More questions, please. Any questions in chat?
No questions in the chat.
So let's thank the speaker again.